Hi everybody, welcome to another video in Calculus 1, section 7.1, inverse function. So this is pretty much a review from what you learned in coarse algebra or pre-calculus, even trigonometry. So an inverse function we denote by of course f to the negative 1, but we usually just say f inverse is inverse if this is a function such that y equal to f of x, then the inverse is equal to x. So pretty much the function will assign an x to a y, and then the inverse will assign y back to x. But in order for that to happen, the function needs to be one-to-one. If we have the function that we have two different x into one y values, for example, we talk about absolute value of x, then the absolute value of negative 1 is equal to 1, and absolute values of 1 is also equal to 1. So in that case, we have negative 1 go to 1, and then 1 also goes to 1. So that is the function. Now the inverse, then we go from 1, we don't know which one do we go back to, negative 1 or 1. So our function has to be one-to-one. I mean 1x go to 1y, and then if we have the same y values, the x values cannot be different. Right? So if there's one y, there's one x. So exactly this is what we say. A function is one-to-one if each values of f of x corresponding exactly one value of x in D. More precisely, it is one-to-one if the y values are different whenever x are different. Of course, the contrapositive to that, instead of saying if the y values are equal, the x values are equal, it says if the y values are different, then the x values are different. Another way to say that is if the x values, so let me just write this again. x1 not equal to x2 implies f of x1 not equal to f of x2. Right. If we want to write that differently, we will say f of x1 equal to f of x2. If the y values are the same, then the x must be the same. Yeah. So if we have the same y values here, the x values must be the same. So this is not one-to-one. So either one of those will be fine. Right. So that is one-to-one function, and only one-to-one function has inverse. And if whenever the inverse exists, it will be unique. And so we have the combination of the inverse and the function gives us back to x, and f inverse is back to y. Whereas it's x or y is not really important. What important here is the inverse and the function will give us back what inside. What is the variable here? So the function and inverse give it back that variable. Right. So one-to-one function has inverse, and when that happens, the combination of the function and the inverse gives us back the original variable. Right. Next, there's a function f of x equal to x squared minus 1 have an inverse. Right. One thing I haven't mentioned is that one-to-one function will pass the horizontal line test. So for example, if we graph x squared minus 1, this function is not one-to-one, because if we draw the horizontal line test here, it will cut the graph at 2 points. So if that is the case, then the function is not one-to-one. because we have different x values for the same y values. That is not one-to-one. Right. So in that case, if it is not, then we just give a counterexample. So the answer here is no. So we can give an example for if we have -1 for x. We put -1 in here. -1 square plus 1. I mean -1 minus 1. And that is 0. And f of 1 square minus 1, that also 0. So different x values for the same y values, it cannot be happening. So two different x values give us one y values, so we don't know which one do we go back to. Right. Now, so we have the function like this. Now, determine the interval on which the function has an inverse. So even though the function on the whole domain is not one-to-one, so it's no inverse. If we only take half of it, then that will be inverse. So in that case, we can say the interval could be the function has an inverse, maybe going from 0 to infinity or -infinity to 0. If we only have half of this, then it is one-to-one because it will pass the horizontal line test. And one more thing. The graph of the function and inverse is symmetric with respect to the line y equal to x. Right, so that is about the graph. Now, in terms of calculation, what we have for the function and inverse is that the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. So that's what we need, because after all, the function, the function and inverse, it will interchange x and y. Right. So let me just write this. Domain of the function is the range of the inverse. The range of the inverse equal to the domain of the function. Right. Of course, the domain for the function is x. The range of the function should be like this. The range of the function is y. So we need to do it here, just switch the x and y. Right. So now we have an example. Find the inverse function of f of x equal to square root of x minus 1 and plot f of x and f inverse on the same coordinate axis. Right. So let's just write out f of x. This is the original function. Square root of x minus 1. Now, let's just graph that and see what happened. Square root of x minus 1. Right. This will go from 1 and the square root. So just make a little table. When x equal to 1, y equal to 0, x equal to 2, y equal to 1, x equal to 5, 5 minus 1 is 4, square of 4 is 2, and so that is square root of x minus 1. Right, notice that the function goes like this. The domain x greater than or equal to 1, right? Because if x is less than 1, then we will have negative inside the square root, which will be imaginary. So the function, even though it's not specified, we need to know that the domain is whatever matters inside the square root greater than or equal to 0. So x is greater than or equal to 1. Right. Now we're going to find the inverse. To find the inverse, there will be two important steps. So to find the inverse, first we interchange x and y, because that's what the inverse function does, and then we solve for y. Right. So before that, we need to know what is y. So f of x here, that is y. Right. The first step is interchange x and y. So we're going to say this y become x, and this x become y. Right. Now to solve for y is the next step. To solve for y is we just square both sides. But remember, every time we square both sides, we need to check the answer. Okay. Because negative 1 square is the same as 1 square. However, without the square, they are not equal. So when we square, we make a negative equal to a positive number. So that's why we need to check. But here we have x squared and square root, and that's x squared equal to y minus 1. So to solve for y, we have y equal to x squared plus 1. So we want to say f inverse. The notation is going to be equal to x squared plus 1. Right. Once again, similar to the x squared minus 1, x squared plus 1 is not 1 to 1. And we also need to check the answer. So what do we check? Right. So remember, the function and the inverse, the domain and chain will be interchanged. Domain of the function is the range of the inverse. The range of the function is the domain of the inverse. So in this case, this is domain of the function. Which will be the range of the inverse. And when we interchange the domain and range, we interchange x and y. So from here, the domain of the function will equal to the range of the inverse. And the range of the inverse, so we interchange x and y. So we're going to write the function is going to be greater than or equal to 1. Which is good there. But that still doesn't help anything. X squared plus 1, of course, greater than or equal to 1. So that's not what we need. We need something better. Right. So the function is square of x minus 1, x greater than or equal to 1. So that is the domain of the function. So, but what is the range? This function, the graph of square of x minus 1 is going to be greater than or equal to 0. So that is the range of the function. The range of the function, which is the domain of the inverse. So here we have y greater than or equal to 0, domain and range interchange, so x become y become x, so here we have x greater than equal to 0. Yeah. So domain of the function is the range of the inverse. The range of the function is the domain of the inverse, and then we interchange x and y. So the answer here is we have the function like that, which is good. However, we need to have x greater than equal to 0. Because that's what we have for the domain of the inverse function. Of course, with that, then we have the one-to-one function, right? So x squared plus 1, like that. Now if we just want the part that is x greater than equal to 0, so we only have the right half of the parabola. So this is where x greater than equal to 0. So in that case, it is 1 to 1. And the inverse says, I'm going to graph this for x greater than equal to 0. When x equal to 0, y equal to 1, x equal to 1, y is 2, x equal to 2, 2 square plus 1 is 5. So the graph like that. And then if we want to draw the line y equal to x, so as you see, we have the function and the inverse symmetric on the line y equal to x. Right. So of course this is nothing new. There's no calculus there. It's just a review of what we have before. But the bottom line is domain and range will be interchanged from the function to the inverse, and from the inverse back to the function. X and y will be interchanged. Right. Now, we have some calculus that go with it. So, it says that let f be a differentiable function and have the inverse on an interval. If x0 is a point at which the derivative at that point is not equal to 0, then the inverse is differentiable at the point y0, and given by this theorem. Right. So pretty much, if we have the function, this is draw differently. This is the function, this is the inverse. So let me draw that again. So this is the inverse. And this is the function. Of course, it's symmetric on the line y equal to x. Now, it says that if we have the function is differentiable and derivative is not equal to 0, meaning that we don't have this as the horizontal line. If this is a vertical, it cannot be vertical line either. So they have to be either horizontal or vertical tangent line. So in that case, there can be symmetric, and we have the tangent line for the inverse function given by that, and will be the reciprocal of the other one. So of course, if we have a horizontal line, if we have the horizontal line for the function, the vertical line will be vertical. If we have the horizontal tangent line for the function, the tangent line for the inverse will be vertical. And of course, neither, if it is vertical, the derivative does not exist. So because we divide by, we don't want that to be 0. That's the point, right? So the inverse function, derivative of the inverse is the reciprocal of the derivative. However, this is y, this is x, and there's a little change in that. So formula is nice and all, but if we can do that without the formula, it will be better. So let's look at this couple. Let's do example. Alright, so we have f of x equal to x cubed. Find the derivative of the inverse of the function. So this is the way I usually do it. F of x, let that be y. Right? Then, according to the inverse, the computation of the inverse and the function will give it back to x. So we will have, if we have the inverse on both sides, by the definition of inverse, it has to be equal to x. Let me just write this. The function and the inverse gives back x, and the inverse and the function also give us back x. And then you said, that's supposed to be y. Well, it doesn't matter. Whatever the variable is, the function and the inverse give it back to that variable. So I could put x, I could put y, whatever the variable here, it will give us the same variable. Right, so yeah, the function is that. Take the inverse on both sides will give us back x. Now, we take the derivative with respect to x. Differentiate. So take the derivative with respect to x. So the right hand side derivative of x is 1. That's easy. The left hand side, well, y is a function of x. As we say here, y is x cubed. So what we will say, derivative, here we'll use the chain rule. So we'll have derivative of that and then derivative of y. So this is chain rule, right? Yeah, derivative of the whole thing and then derivative of the parentheses, which is y prime. Since we're going to solve for the derivative of the inverse, we divide by y prime on both sides. Right, so that's good and all, but what is y prime? Now we can go back, since y is equal to x cubed. So y prime is 3x squared. So that is 3x squared. Right? So we have the inverse and then take derivative will be the inverse, derivative of the inverse, and that, so 3x squared. The only problem here is this is the function of y and this is x. So how can we rewrite that in terms of y? The answer must be in terms of y, right? So x squared. If we can write this in terms of y, that would be good. We have to write the answer in terms of y, because we cannot have the y and then end up with something x. Now, if y equal to x cubed, then we can solve for x. That will be cube root of y is equal to x. So we can substitute that in here. 3, and then we have cube root of y square. If we rewrite that, we can have 1 over 3 and y, the power on the top, root at the bottom, index bracket at the bottom. Right, so we have derivative of the function y is equal to function of y, which is good. And then if we want to write the answer, we can write the inverse in terms of x. If we change y to x, then we will have 1 over 3 x to the 2/3. So what do we do? I'll take the inverse on both sides, write the original functions y, take the inverse on both sides, and use implicit differentiation and solve for derivative of the inverse. But that will be in terms of x though. So we write that x in terms of y. So whatever the derivative should be in the same variable. And then at the end, if we want that in terms of x, we put x and x here. And that's what we have. Right, so this is one way to do it. The other way, of course, we can just do that directly. So since y equal to x cubed, I should not write that. F of x equal to x cubed. If we replace y into x cubed, and then we interchange x and y, that gives us x equal to y cubed. And then when we solve for y, we'll have y equal to cube root of x. When we check the cube root on both sides, do not put plus or minus. So we found the inverse. So the inverse function is equal to cube root of x, which is x to the 1/3. Then we check the derivative of the inverse. It's 1/3 x to the negative 2/3. Yeah, just power rule. And then bring that to the bottom. And then you'll say, why don't we just do it like this? Why do we have to use the inverse function too? Well, the problem is sometimes, even though if we can solve for the inverse, if the inverse is complicated, that might be a problem. So when we go to section 7.5, when we have the inverse trigonometric function, we're going to use the same thing. And that will be helpful even though we can find the inverse. But we might not be able to take derivative, right? So like for example, we have the sine equal to something, then we have inverse, a sine inverse. Then how do we take derivative of something that we don't know yet, right? So if we cannot take the derivative of the inverse, but we can take the derivative of the function, then that's what we do, use the inverse function theorem, right? In this case, it could be either one, because we can take the derivative of the inverse, right? Bottom line is, replace the function by y, take the inverse on both sides, and find the derivative implicitly, right? So let's find the derivative of the inverse of this function. So first, we write y equal to 2x to the 5th minus 5. Right. After that, the inverse on both sides give us back to x, because that's the definition of the inverse. So we take the inverse on both sides. And by definition, the inverse of the function with respect to x. Yeah, later on, of course, we will solve for the inverse, but for now, that's what we have, right? Now, assume y is a function of x, we differentiate with respect to x. Yeah. I want to use some space over here. So differentiate with respect to x. Right. So since this is the function of y, when we take derivative on the left hand side, we have to take derivative of y, because we take derivative with respect to x, and y is a function of x, so we have to have derivative of y. Or we should say it, parentheses, yeah, derivative of the whole thing and derivative of the parentheses, which is y prime. Right. Derivative of x on the other side just 1. So we can divide the y inverse, the derivative of y on the other side. So to get to the inverse, derivative of the inverse as a function of y is going to be 1 over y prime. Usually it is like that because that's what the theorem is about. That's the inverse function theorem. Right. Now, and then if y is equal to x to the 5th minus 5, then y prime is equal to 10 x to the 4th. So y prime is going to be 10 x to the 4th. Right. So the derivative of the inverse is a function of y is 1 over y prime, and y prime we can solve easily, 10x to the 4th. Now, since this is y, we need to write the answer in terms of y, in terms of the same variable. So in that case, we have to know what is x equal to in terms of y. So that's where we find the inverse. All right. Y equal to 2x to the 5th minus 5. First step is interchange x and y. So x becomes y and y becomes x. Now we can solve for y from here and then substitute back to it. Right. So solve for y. I will plus 5 on both sides. And then divide by 2. And then since this is the 5th root, an odd root, when we take the square root on both sides, there's no plus or minus. So we have y equal to the 5th root of x plus 5 divided by 2. And I can substitute that back in here for x. Right. Never mind, that was a little confusing. Yeah. So we don't find the inverse here. Sorry. Don't need to find the inverse. We need to know what is x equal to a function. Yeah, we need to write that in terms of y. So in that case, we just solve directly Yeah, we have the inverse, which is good, but we don't need to do like that. We have y equal to 2x to the fifth minus 5. Right? Now we just need to write that in terms of x in terms of y. So again, y plus 5 and then divide by 2 and then take the fifth root. Right. So it is important that we know when we write this, the answer should be in terms of y. So we're going to have x is equal to that. So we have to have fifth root of y plus 5 divided by 2 to the fourth power. Right, so don't do the inverse. Don't interchange x and y. Just go ahead and solve for x because we need x in terms of y. Right? So yeah, when we have this, of course, we can take the derivative of that directly. But I said, don't need to interchange x and y because we need x as a function of y. Right? And then we can write power on the top, index bracket at the bottom. Right. So whenever we don't need to find the inverse here. Whenever we write the answer, remember the inverse is a function of y. The answer should be in terms of y. So even though we have x, should solve for that. In this case, x equal to fifth root of y plus 5 over 2. Then the fifth root of that. So we substitute in, and that's what we have. Now if we have derivative in terms of y, is this function in terms of y. If we go back to answer the question, we can just write everything in terms of x. Right? So yeah, usually if the question answers, if they want a variable x, we just need to give them the answer in terms of x. Because the way we solve for it, we have the inverse in terms of y. So the answer will be in terms of the same variable. So if they have the same variable, we can go back and switch back to x. Right. Yeah. Because of that might be confusing, so I will do one more example. Just make up on the fly here. So example. Find derivative of the inverse if the function is equal to, let's say we want to choose something that is 1 to 1. So let's say cube root of x plus 1. Right. Right, first of all, let's start with let y equal to that. Now, apply the inverse on both sides. when we apply the inverse on both sides, it will give us back to the variable x. Right. So let's just write. We will write f inverse of y equal to f inverse cube root of x plus 1 give us back to x. Now we differentiate with respect to x. So derivative is going to be derivative and then derivative of the parentheses. Inside we have the inverse. Derivative of x is 1. So we just have 1 divided by the inverse. At 1 over the derivative. Right. Now, this, if we write, okay, now do the scratch work here. Y equal to cube root of x plus 1, which is x to the 1/3 plus 1. So we take derivative. Give us 1/3 x to the 2/3. Sorry, negative 2/3. Right. Never mind, different. Right, derivative, it will be 1/3 x to the negative 2/3. Now, divide by 1/3 is the reciprocal 3 over 1. Right, let's just write like that. And then x to negative 2/3 move from the bottom to the top, become x to the 2/3. So that's what we have. So we're going to have 3x to the 2/3. Now, here's a little problem. This is y, the answer in terms of x. So we need to write that the answer in terms of y. Right, in that case we have to say x is equal to what? Right, y equal to cube root of x plus 1, subtract 1 on both sides. And then we cube both sides. When we cube both sides, we don't need to check the answer. So x equal to y cubed, y minus 1 cubed. And I can substitute that into here. So the answer will be equal to 3. Instead of x, I will have y minus 1 cubed. And then there's still the power 2/3. So which gives us 3 times 2 over 3. 3 and 3 cancel out. We have y minus 1 squared. Right? So the derivative of the inverse in terms of y is that in terms of y. If we want to switch back to variable as x, then we change that into x. So consistently, if the variable is y, we have y. If the variable is x, we have x. Right. So again, just like the last one, we don't need to solve for the inverse. we kind of do the same thing, but we need to write what is x equal to, because the answer is supposed to be in terms of y. Well, if you find the inverse of this function and you take the inverse, that will be simple, right? So if that is the function, you can find the inverse. Once you have the inverse, we can take the derivative directly, right? But that's what we do. The derivative of the inverse is 1 over the derivative, but just need to change that in terms of the same variable. And to do that, we need to solve for x, and to solve for x, that's what we have. So substitute in, and so derivative of the inverse in terms of y is in terms of y, which is good. Now if we want to switch to other variable, replace x here and x there, that's what we have. Right. So that is another example. So most of this, the problem here, we will not just find derivative of the inverse like this. We apply to use this theorem to some function that we don't have derivative directly. For example, the trigonometric function. So we use a lot of this in section 7.5, which is the last section that I want to go over. But other than that, this is the essential inverse function theorem. Just make sure that the variable is the same as that. Right, I stop this section here. As always, thank you for watching, and see you in another video in Calculus 1.